So I just want to cover some last topics in geometric optics and bridge us into wave optics with the topic of dispersion. And basically this is the stuff that we've been kind of sweeping under the rug a little bit, some approximations and some phenomena that you know about, but we haven't spoken about. So first, spherical aberration. The spherical aberration of a lens is why they need to be thin. So over and over we said thin spherical lenses, thin spherical lenses. Well, why do they need to be thin? So if you had a really, really good middle school teacher who taught you stuff about conic sections, you may actually remember this. So it turns out that circles actually don't have a focus. This is not a statement about physics, this is a statement about geometry, where if I just drew a circle or part of a circle and I had a whole bunch of rays coming in parallel to each other and they bounced off of, in this case, a spherical mirror, and I drew the normal coming from the center of the mirror, they wouldn't actually go through a single point. There is no focus. They would actually get smeared out a little bit. And I can limit that by making the amount of the mirror that I light up smaller and smaller and smaller. So because this isn't perfectly true, circles and their 3D counterpart spheres actually do not have a focus. There will be a slight kind of mushiness to any real image. This phenomenon is called spherical aberration. So it's actually true for spherical lenses as well. If I have a whole bunch of rays coming in parallel, they're going to interact with the spherical side of the glass on the near side and then again on the far side, and those won't go through a single point. They'll also be spread out through not one focus, but kind of a focal blob. So this effect again gets limited if I have a thinner and thinner and thinner lens. So how would this actually manifest itself? If you're a photographer or know a professional photographer, they might actually have talked about spherical aberration. This is how it would show up on a picture if I had a really kind of thick, gross lens. Is I could put this guy's nose in focus or ear or the edge of the image. I couldn't put the whole thing in focus at once. So basically, if you look at the ray diagram on the left, where I am on the lens would determine where my focal point is. So center of the lens has a focal point, and then as I get farther and farther out, it has a different focal point. So basically, can't put the whole thing in focus. And again, this is limited by me just taking a very thin lens. So because we live in the 21st century and have modern manufacturing techniques, what you can do is you could get a parabolic mirror or a parabolic lens. And if you do remember your classical geometry, if you ever taught it, parabolas actually do have a single focus. It's absolutely geometrically true that light coming in parallel will all converge at a single point for a parabola. So essentially what's going on is that, if I cut the bottom cap off of this parabola just a tiny bit, it's kind of visually indistinguishable in between a sphere. So spheres look enough like a parabola if you cut that thin enough that essentially it has a focus. So again, we live in the 21st century. You can absolutely buy parabolic mirrors, and the point of buying a parabolic mirror, in fact, satellite dishes are parabolic mirrors, which is pretty easy to make for things that reflect radio waves, is that these actually will focus at a single point. So these will be better, and as you can tell, they're not prohibitively expensive. But that's the point of a parabolic reflector. It truly has a focus. So yeah, again, this is a phenomena that I just want you guys to be aware of, but for all the lenses that we'll talk about in this class, thin spherical lens means you can approximate this thing as having a single focus. And again, the reason you can do that is one of these is parabolic, the other one is spherical, I guess, by virtue of the one on the right having a focus. It's got to be parabolic. But if I just look at them, I honestly can't tell the difference in between that spherical curve and the parabolic one. So close enough. And I will not ask you guys any questions about parabolic mirrors and foci. So what we will talk about is this. So this is a phenomenon that you absolutely know a lot about, dispersion. Everybody's seen white light coming into a prism, whether a real image or an artistic one, and it being broken up into a rainbow of different colors. So now that you guys know some of the lingo, what is it that must be happening? So what needs to be true about the light or the prism to make this phenomenon actually work? So it turns out that this is the lie, that when I said that glass or diamond or honestly just about anything else aside from vacuum has an index of refraction, that's not true. Those things have an index of refraction, one single index of refraction. No, in fact, because you're seeing this, you're seeing the blue light bend more than the red light. Blue light needs an index of refraction, and red light needs a different index of refraction, and each color has its own personal index of refraction. Yuck, what a mess. So this is the bridge into treating light as a wave. So this is what's called a dispersive phenomenon, where dispersive waves, the wavelength of the wave itself tells you what its speed should be. So this is true about water waves as well. Water waves are dispersive, which is why when they go from deep water to shallow water, they roll over on themselves and crest and you can surf them. So light to some degree is like that when it goes through media that isn't a vacuum. And I'm just putting this little n equals n lambda out there so you see it now before we get into wave stuff. Lambda would be the wavelength of the light. And in fact, this prismatic effect is how we know that there are other wavelengths of light in the first place. So back in, I don't know, 1790 or 1800, an astronomer, Frederick Herschel, was trying to figure out if blue light had more energy than red light. So what he did is he took some white light and he broke it up with a prism into blue light and red light and yellow light, and he basically held thermometers in each type of light and saw how quickly the thermometer would heat up. And he left one of his thermometers out in the infrared section, and lo and behold, the infrared, the thermometer out past the red light was heating up too. And he deduced from that that there's a type of light that the human eye can't see, but it still exists. And it was able to heat up the thermometer. So a pretty good experiment for 1800. So this is something we will talk about in the context of geometric optics because we can ask some questions and it is important. So we did a prism problem just with white light. We can return to that prism problem and its sneaky geometry and maybe ask about blue light versus red light. This describes a whole wide range of other phenomena. So in fact, now that we've talked about dispersion, reflection, and refraction, we can talk about why there are rainbows or double rainbows, because that is absolutely a dispersive, refractive, and reflective effect. And in fact, this is why the sky is blue. So it's basically a dispersive phenomenon. Although usually people talk about it more in the language of quantum mechanics because you kind of care that nitrogen really scatters the blue light strongly. But the short answer is that the sky is blue because of dispersion, is that nitrogen bends blue light more than yellow light or green light or red light. So we'll stick to rainbows though. So this is what's going on in a single rainbow. So you have to be with the sun at your back, sunlight comes in over your shoulder, and then it interacts with mist or water droplets. First, it goes into a water droplet, at which point it goes from air to water and it refracts. And then it bounces via total internal reflection off the backside of the water droplet, so it reflects, and then it makes it out the near side of the water droplet, going from water to air, then it refracts. So you get one refraction, one reflection, and another refraction. That's a lot of traveling and bouncing. So because water is dispersive, what's going to happen is on that total set of reflections and refractions, red light's going to be bent differently than blue light. And so when the white light goes in, has all this stuff happen to it, then it comes back out after reflecting on the same, going back in the direction it came, the blue light and the red light are going to be bent by different angles. And because water droplets are spherical, it doesn't matter how big they are, you can always work out the geometry, and it always turns out that blue light will leave it about a 40-degree angle and red light will leave it a 42-degree angle. So that's enough to visually notice. So if a water droplet is 20 degrees above your horizon, you're an observer standing on the ground, what you're going to see is reflected and refracted blue light. But for the water droplets that are 21 degrees above your horizon, you're going to see the red light. So you're only going to, what you're seeing in some sense is just the part of the light that gets refracted right into your eye. if it's 20 degrees above your horizon, blue. If it's 21 degrees, it's red, and then in between. And that's a big enough of an angular dispersion that you can see it. So what's going on with the double rainbow? Why don't we explain double rainbows since we're here? Of course we should. The difference in between a primary rainbow, which is one refraction, one reflection off the back of the water droplet, and then a second refraction to get out, a secondary rainbow, or the double rainbow, is two reflections in the middle. So sunlight comes in, refracts not once but twice, and then refracts on the way out. So because of the second refraction, double rainbow is actually inverted. So it doesn't go from red on the top to blue, it goes from blue on the top to red. And you can see that faintly in this picture. You can see the double rainbow, and it's inverted. And of course, less light comes out. They're fainter because fewer rays of light will experience this more complicated sequence of refraction, reflection, reflection, refraction. So this is also, if you substitute out water droplet with its simple geometry and slightly dispersive medium of water with gemstone, which has a complicated geometry and a very dispersive medium like diamond or sapphire or emerald, you get why we pay a lot of money for these things. So just look at this as an actual picture. It's a very large and expensive diamond, and you can see exactly the same sort of thing going on. So white light from some place is going into the diamond. It's reflecting around, so the faceting of a gemstone is basically designed to have as much reflection as you can imagine happening, and then because of all that reflection and refraction, the white light is split up into rainbows. You can see rainbows everywhere. Finally, it kind of lucks its way out of the gemstone, and you see the split up light. In fact, regardless of how the top is shaped, the bottom faceting, so they all have this kind of cone at the bottom, that's designed so that when light comes from the top down, it's going to be more likely to totally internally reflect. So if that was flat on the bottom instead of shaped like a V, it would be more likely to just leave the other side and it wouldn't be as pretty. So when you have pillow cut gemstones like big emeralds, the reason it's flat on the bottom is, well, they're green, so you just want to show off the color. Whereas clear gemstones like diamond, you want to do this. Okay, so that's pretty cool. I don't think you needed physics to appreciate rainbows and gemstones. What does this do for us? So there's another effect in lenses that's kind of important. So what consequences does this have for a lens? So think about the lens maker's equation for a second. And what this is a chart that we'll refer to. Clearly it's got wavelength on the bottom, so we're talking about light as a wave. And this would be the index of refraction for some materials. And you can see it changes pretty drastically, especially around blue light. So I'm thinking about the lens maker's equation, and part of it has the geometry of the lens. That's just the geometry of the lens, those radii. But then I've got this n. So if n is different in between blue and red, what does that mean about the focal length for blue versus the focal length for red? Yeah, so we have another type of aberration. So spherical aberration is the geometric effect where the lens itself, if you're coming into the top or the bottom of the ray, you have a different top or the bottom of the lens versus the middle, you have a different focal length just based on the geometry. So there's a thing called chromatic aberration, which regardless of how you're coming into the lens, and this would be true of a parabolic or a spherical lens, is that because the thing itself is dispersive, glass treats blue light and red light differently. The blue light's going to be bent more, the red light's going to be bent less. Blue light will have a focus that's closer to the lens, and red light will have a focus that's farther out. So this is the idea of chromatic aberration. And astronomers, again, because they really care about precise lenses, they have very few photons to work with, and they have very big things to bend them with and collect them. They care about this stuff a lot. This is obviously a stunt lens. You would never actually want to take like a baby photograph with this or something. The parent would be like, what'd you do to my kid? So this shows both spherical and chromatic aberration. So you can see that the colors that are from the white light are being treated differently. So you see the blue and the red, and they seem to be on different focal planes. And then you also see the fuzziness, especially at the edges of the lens. So that would be from the spherical aberration as well. So you have both of these. You can get rid of one with geometry. The other one, you're kind of stuck with if you have any sort of refraction. And we can ask some questions about that. So this will be a quasi-refraction demo. So here's a prism, and it's not going to be particularly convincing if I put light through that and try to get it into the camera. So I am going to cheat a little bit. Basically, for all intents and purposes, this is a diffraction grating. It's a bajillion little prisms. So this is finely ruled, and there are all these little kind of mini stripes like this, and it acts in the same way. So this will actually presage a topic in wave optics as well. So here's a lamp. It's actually full of helium that I'm beating up with electricity, and I'm going to pass it through a prism. And what's going to happen is you guys are going to see this kind of neat quasi-rainbowy effect. It's not really a rainbow, but what you're seeing is the light being broken up into its constituent colors. So this nice kind of peachy color, and then when I go out here, you can see it broken up into a bunch of actually discrete wavelengths. So this is not a rainbow. It doesn't have all colors in it. It's just got a couple of particular colors, and we'll explain that when we get to quantum mechanics a little bit. So the other thing I can show, which would be more of a classical dispersion demo, is here's some white light. See, white light. And I'm going to bounce the white light off of that dispersion grating, and what you can see is that this definitely breaks up into its constituent rainbow colors. Right? So this is a dispersive element. It's not doing it in the same way that a prism would be, but it's just really hard to do this with a prism. I'll give it one try, and then we'll give up. I have no idea if that came out. I sincerely doubt it. Okay. So of course what you're really wondering is, what could you possibly ask me on a quiz? So the good news for dispersion is that dispersion problems are really just multiple plain old ordinary refraction problems. So let me get this gently out of the way without burning my fingers on it. Let's just say that you have a comically oversized diamond, and you just want to measure its indices of refraction, which no longer can we say it's got an index of refraction. What I have to ask you is, well, which one, blue or red, or a particular wavelength. And bear with me, this is a little bit implausible. I've got a giant diamond with a flat surface, right? And I've got air on this side. And honestly, I'm just going to do not one, but two separate calculations. Kind of stickler about the colors, so I'll get my red whiteboard pen. And I've got white light coming in, and we'll put white light coming in, and we'll give it an angle, so theta incident. And in order to do this right, because usually these dispersive so-called chromatic index, so basically what the difference in between the blue and the red index of refraction are, they vary so subtly that I'm going to go out to 4 sig figs just so we can get a somewhat reasonable answer. Right? But that's theta I, and I'm making it 35 to a part in 100. And then what I have on the far side, because diamond and air and water and everything else, this is the lie part, I'm going to have blue is going to have its own personal index of refraction. So we'll call this theta blue refracted. And red is going to have its own personal index of refraction. So the refracted angle for red. And it turns out maybe this is 13.77 degrees, and it turns out that blue might be 13.48. So this would just be a pure measurement. Like I'm measuring this and I want to find out what the index of refraction for blue and red light are. And that's it. It's just multiple instances of the stuff that you already know how to do. So dispersion is a really cool phenomenon. It has all these like neat effects that you can see in the form of rainbows, double rainbows, supernumerary rainbows, which we're not going to talk about, but you should look up. But honestly, when push comes to shove, all you have to do is use the law of reflection and Snell's law. Maybe you have to do it twice. Okay, so I have n air sine theta I equals n refracted for blue sine theta blue r. And know it, don't know it, know it. So that's, I'm going to just, a little bit unnecessary, but I'll do it anyway. Sine theta 35.00 degrees is n blue. Oops, this is just n blue. Sine theta refracted blue, which is 13.48. And nothing special, again, this is just math. And blue, I should put this to 4 sig figs. I got 5, 4, and 4. A little bit of a departure from the online homework, but you'll need it for this. And I can't do that math in my head, so 2.462. And then likewise for n red, same angle goes in, but because this has a different index of refraction, we get a different angle out. And I'll just like dot, 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 because it's basically solved the exact same way. The only difference is this number is 13.77. I would get n red equals 2.4 still, and then 410. Okay. So what people will do, and this won't make a ton of sense right now because we haven't talked about light as a wave, is that what people will quote is, and because this is a non-calculus based class, they'll quote the rate of change of the index of refraction relative to wavelength, and this will be a tiny, tiny number typically if you're talking about like meters or even microns, millionths of a meter, because light has a tiny wavelength, which is why we've been doing geometric optics. But again, the good news is that dispersion is a cool phenomenon, but all of these things just rely on two things that we've already talked about, Snell's law and the law of reflection.